this lecture, we will cover section 7.2 of the prescribed textbook, which deals with tries. Note that this is the last section that is going to be actually examinable out of chapter 7 for this course. So this is the last section of chapter 7, then we will move on to chapter 8 in the next lecture. Alright, so most M-way trees that we have considered usually store the entire key in the nodes. The only difference to that were the prefix trees that did not necessarily store the entire keys, but rather found the smallest prefix that was necessary to tell the difference between the key on the left-hand side and the key on the right-hand side, which obviously saved some space. Another similar M-way tree that also tried to save space by not storing keys unnecessarily were the bit trees that essentially only stored the digits. Difference bits that allowed us to tell the difference between two keys on a binary level. However, it turns out that storing prefixes is not always easy, and as you add more items, more keys to your tree, as you have to split the nodes, it turns out that maintaining the prefixes can be a mission all on its own. Let's do a quick example. Here is a prefix b plus tree, where, as you can see, just the minimal prefixes are used, and in this particular example, a single first character was sufficient to tell the difference between the leaf that stores the words and, aunt, and ant, as well as the node next to it, leaf node next to it, that stores the words bar, barred, and bear. However, suppose we insert another word into this prefix tree. Let's say that word is bell. Bell is obviously going to belong in my B leaf node, but as you can see, that leaf node is full, it's at maximum capacity, so I have to split the node. What is the result of that? The result of that is that now I will have two leaf nodes that both store words that start with a B inside of them. So clearly, just the first character of the word, just the first letter, will not be sufficient to tell the difference. So we will have to go one level up and update our prefixes to perhaps now store two characters rather than a single character. And this is exactly the prefix maintenance that we speak of, that we say can be a complex algorithm all on its own. Today we are going to discuss tries. The name comes from the word retrieval, but if we read tries as trees, that would be quite confusing, so they are pronounced as tries. And these are M-way tree structures which actually never explicitly store the entire key. So the point here is to store just the minimal necessary characters and also store them in such a way that maintaining the prefixes would not be too complicated. So instead of ever directly storing keys or their prefixes, what we are going to do is we are going to find out what is the minimal smallest primitive building block that makes up the keys and the prefixes. And then we are going to use those minimal building blocks to put the keys together. Tries are extremely useful in the context of English language, of language in general. So throughout this lecture, we are going to be using just the English words as the example of the kind of stuff you would want to store in a try. So essentially, every single word, a string, is obviously made up of characters. Thus, a single character is going to be seen as this primitive building block. So what we are going to do is we are going to store the first character of the words in the root level of the tree. Then the second level will store the second characters, the third level will store the third characters, etc., until you have stored all of your words. And in this case, if I want to extract or find a particular key, I will not be looking for that key in a particular node. Instead, I will need to traverse the tree, and that traversal path itself, the trajectory that I took through the tree, would represent the key. Let's say, for example, I'm trying to see if the word bear is stored inside of the tree. I will go to the root node, find the first character of my word bear, which is B. B is there, so I know bear is probably stored in my side of my trie. I will then follow the points associated with B to the next level of the tree, to the next node. I'm looking for bear, so now I need to find the pointer associated with E, and I find it. It takes me down to A, which takes me down to R. And as you can see, these four characters individually stored inside of my nodes together form the word bear, and that is how bear is stored. It's basically distributed across 4 levels of the tree, in this case, of the trie. So let's try to get more specific. Let's think about how we are going to implement this. Well, obviously, words are nothing else than the combinations of characters. So if I want my trie structure to be universal, the easiest thing to do is to say every single node will be essentially an array of a fixed size, and that array will simply store the entire available alphabet. And then if every single node stores the entire alphabet, I should be able to create any combination of characters that is a valid word, that is a valid key in my particular trie. For simplicity's sake, I'm not going to put the entire English alphabet into every single node. Let's say we are working with a limited alphabet of only 4 characters, A, B, D, E, and R. Great, and now that we have defined the alphabet, now that we know what the options are, we can create fixed-sized arrays, and the non-leaf nodes will essentially be these fixed-sized arrays where with every single character in the alphabet a pointer is potentially associated. And then if a pointer is null at any point in time, then that will tell us that that particular combination of characters does not form a valid word. However, if it's not null, it will tell us that the word is actually present. This particular combination of characters does in fact correspond to a valid word. And finally, the actual valid words are going to be stored as the leaf nodes inside of the trie. So you can think of your non-leaf nodes as this index set that essentially allows you to search the trie. And once you've searched the trie, once you've gotten down to the bottom level, if you end up with a null pointer, you know that what you're looking for is not a valid key, it's not stored in the trie. On the other hand, if you have found a leaf node that is a valid word, then you know the word is actually present and that key is indeed stored in your trie. So how do you search a trie? You obviously start at the root node. What we are going to do is we are never going to try and compare the entire key to an entire key, because remember, the key is now broken down into characters. So we are going to be doing the search character by character. Take the first character of the key that you are trying to find and match it against the corresponding character in the root node. Let's say once again we are searching for bear. So we go to the root node and we find the character B, because that's the first character in bear. We then check, does the pointer associated with B lead somewhere, or is it null? If it's null, I can conclude that the bear is not a valid key. It is not stored in my trie. However, in this case, as you can see, B does in fact have an arrow associated with it. It's not a null pointer, so I can go to the next level of the trie. Now that I'm in the second level of the trie, I will be looking for the second character of bear. So I'm looking for the character E. Once again, find the character E, see if the pointer associated with it is null or not null. If it's null, you're done, just assume the key is not there. If it's not null, follow the pointer. In our case, it is not null. We're going to follow that pointer. You now arrive at the third level of the trie. So we will be matching the third character of the word bear. So it's the character A that we want to match. We find A, and once again we check where the pointer leads. And the pointer, as you can see, leads us to the leaf node, which confirms that bear is a valid key and it is stored in the trie, and we have successfully found it. Let's search for something else. Let's search for beer. Once again, B is going to take you to the second level, E is going to take you to the third level. As you can see, so far we are following the same trajectory. That is because beer and bear share the first two characters, so they share that prefix. But that's not a problem at all, because we can still differentiate between these two words on the third level of the trie, where A is going to lead us to bear and E is going to lead us to beer. Okay, that's all good and well. Let's do another example. What about the word bee? Bee is this cute little insect, very useful, pollinates the flowers. It's definitely a valid English word. We want to be able to store it inside of our trie. So if we search for bee, where exactly is it going to take us in this case? Bee will take you down to the second level, is going to take you down to the third level, and then inside of the third level, as you can see, B-E-E is actually associated with the word beer. So it's almost like that space is already taken. Therefore, if we wanted to store B, currently there is no obvious way of actually doing that, right? We've already taken that prefix BEE for beer, it's occupied, so where is the B supposed to go? Let's find a solution to this problem. This is actually quite common. Generally, quite often words in any language would have similar prefixes, and sometimes the prefix of one word might be a standalone word on its own. In this case, B is indeed a prefix of beer, but also it is a valid independent word with a completely different meaning, and we should be able to store both. In order to accomplish that, we are going to expand our available alphabet. We will not just store all the valid characters, we will also introduce a special character known as the end of word character. And for tries, we typically represent it with the hash symbol. So, how is it going to work now? For the beer, once again, B will take you down to the second level, E will take you down to the third level, and in this case, we will not associate BEE directly with beer, we would rather add an extra node, the fourth level, where R can now be associated with beer, so we have essentially spelled the entire beer as a word inside of our trie, and then B, in this case, can be associated with the end of the word character in the same node. So for the B, we once again are going to start at the beginning, right? At the very same B in roots. It will take us down to the second level. It will take us down to the third level. Then for BEE, there will be a pointer, and in this case, this pointer is not associated with one word or the other. It rather leads you to a non-leaf node, this purple node that I've drawn. And inside of that purple node, you can differentiate between the word that ends here, B, by associating it with that hash symbol, and then for the beer, you can just spell the last character of that word. So this end of the word character now allows you to store words that happen to be prefixes to other words. Okay, so if we store these prefixes so well, we've essentially spelled out the entire beer and B. Question is, why do we have to repeat ourselves and then once again store the entire key inside of the leaf node? Is that really efficient? Well, the answer is it definitely is not efficient. So perhaps if you have already spelled out the prefix, maybe all you need to store in the leaf node would be the suffix of the word. In other words, just the last couple of characters that are maybe unique to that word that are not shared with anybody else, but you don't have to store them in a trie, you can just store that ending of the word inside of the suffix. Let's do a specific example. So we know that B and beer are completely spelled out by the trie itself. So just to tell the user that this is a valid word, we can make sure that R, this very last character of the word beer, is not associated with a null pointer, instead, the pointer is not null, but it points to an empty string. In other words, there is no suffix necessary, the entire word has been spelled out. And then for the B as well, the entire B word has been spelled out, so for the end of the word character, we do not store a suffix because there is no suffix, we just store an empty string with a not null pointer just to signify, to tell the user that this word is in fact valid. However, for some other words, let's consider the word dear, for example. We start with a D, it takes us to the second level, E is going to take us to the third level, and this is as deep as we need to go to differentiate between dear and dead, the two words starting from D that I'm storing in this particular try. So E is going to lead me to the leaf node, and as you can see in the leaf node, I do not spell the entire word dear, I just store that suffix, the last character, which was not explicitly stored inside of my non-leaf nodes of the try, but nonetheless is necessary to form the entire key. So now that we have spelled the entire word dear with 3 characters stored in non-leaf nodes and the last character represented by the leaf node. And in this way we do not waste too much space by repeating ourselves in the leaf nodes. Perhaps at this point in time we should take a quick break and ask ourselves, why would you want such a structure? Obviously, not maintaining prefixes all the time is an obvious benefit, but what are the potential useful applications of this very specific M-way tree? In case you have not guessed it yet, the most useful applications would probably be spell checking or automatic word completion. Essentially, a try allows you to store the entire dictionary of the English language, for example, or any other language. It's up to you what alphabet you decide to use. And then, of course, if you store all the valid words, it allows you to check when somebody is typing something, it allows you to check whatever the person is typing against your try. And if at any point in time the person makes a spelling mistake, you will immediately be able to tell them, hey, this word is not present in my try, therefore you are probably misspelling it, you are doing something weird. On the other hand, if they have typed a prefix far enough, you can always allow automatic word completion. You will be able to guess perhaps the suffixes just by the prefixes entered by the users. So this is just a very good, a very efficient representation of the human language, which is extremely useful in spell checking scenarios, automatic word completion scenarios, and any linguistic related scenarios. Obviously, as humans, we work a lot with the human language, so a structure that is optimized for human language makes a lot of sense. Of course, it will find a lot of uses. All right, so let's do some algorithms. Let's consider insertion into a try. So this is, you are given a try. As you can see, in this case, for simplicity's sake, I decided to not compress the leaf nodes into just the suffixes, just so that you can see exactly which words I am actually storing. So maybe this is not the most efficient, but I think this is just an easy example to work with. How do you insert? First of all, you obviously start at the root. Let's say you are given some key and you want to make sure that this new key, this new word is actually added to your dictionary. We're going to search for that word. And essentially, we're going to search until either we find a leaf node or we find null. Let's search for the word red. We start at the top, we find R, and we realize, the first character of red is R, we realize that R is actually associated with a null pointer. So far, we have no words starting from this prefix. And well, this makes our job quite easy. Since R is a null pointer, we can simply create a leaf node red and just store a pointer to that leaf node inside of R. So red has been successfully inserted. It was a very, very simple, very simple operation. You just create a leaf node, you update the pointer, done. Okay, What if you reach the end of the words simple? Let's say we are inserting B. In this case, assuming B is not actually there. Once again, search for B first. So start with the B. B is going to take you down to the second level. You find E, you realize it's not null. As long as it's not null, you must keep following it. Okay, B takes you to the next level. You realize that E, B, E is also not, the second E is also not null, so you follow it once again. At this point in time, you have reached the end of your word. You have exhausted the options. You've matched all three characters. Therefore, the only option for you is to go to the end of the word simple in that node, that where you ended up, and attach the B right there. Excellent. And finally, if you end up in a leaf node and you realize that the leaf is not null, so let's say, we'll do an example now. You basically arrive at a place where your prefix is already used up by different words. What you will then need to do is actually match your word against the word which is currently in the leaf, find their common prefix, and add as many non-leaf nodes as necessary to be able to separate the two. Let's do an example. Let's say we are inserting the word read. We follow the pointer of R and it immediately takes us to the leaf node. Essentially, prefix R is already taken. That place is taken, we can't just place read there, somebody else is sitting there. So we have to resolve this conflict. And we are going to resolve it by matching the current leaf node read against the word that we are inserting, read, character by character, to figure out how many extra nodes do we need to add. So let's put them right against each other and see what is their common prefix. They both start from R. We figured that much, otherwise we would not have had this problem. How far does this match go? Well, clearly, because they match in R, we can't just have R pointing to either of them, so we need to immediately add an extra node that's going to be a separator. Since, one word starts with R, another word starts with R, we need to add a second level that allows us to maybe differentiate on the second character. However, the second character for read and read also matches. So RE is not enough. We can't just associate RE with read as well as read. So we need another separator. Therefore, we are going to add another node on the third level. Once again, keep matching. D and A, here they do not actually match. That is good news. This means that we have gone deep enough. We can now easily draw the line between read and read. So RED is going to be associated with read, and REA is going to be associated with read. So we've arrived at such a point in our try where there is no ambiguity. Excellent. We have successfully covered all possible insertion cases inside of the tries. Let's talk about the efficiency of tries. I told you this is an efficient way of storing the entire dictionary of words in the English language. Let's first of all consider how deep the tries can get. And I'll immediately give you the formula that always works. If you want to know the depth of the try that is necessary to store your given set of words, your given dictionary, all you need to do is calculate the longest common prefix and add 2 to it. Let's try to unpack this formula a little bit. So consider the words that are currently stored at leaf nodes inside of my try. What do you think is the longest common prefix? Remember, common prefix is the set of characters that match across the words. It's probably not a surprise to anyone that B and beer are the ones that had the most conflict, right? We even had to use the end of the word character. So the longest common prefix that you can find in this particular dictionary is B, 3 characters. So the length of the common prefix is 3. What exactly does that mean? That means that just the 3 levels, B, E, and E, will not be sufficient to differentiate between them. So if you have a common prefix of a particular length, you know you will need to add an extra node just to be a separator between the two words, bee and beer in this case. And finally, the leaf nodes also count towards the total height of the tree. So because we know in addition to this one separator node, non-leaf node, we will also have to add leaf nodes for both of the words that share this common prefix. That is where the extra one is coming from. So longest common prefix plus 2, the 2 in this case stands for, first of all, the separator node between your two words that share this longest common prefix, and the second of that 2 is for the addition of the leaf nodes to store the actual keys at the end of the day, or the suffixes if you're trying to be very efficient. So this is how the height of the trie is calculated. How does this translate to an actual human language? Let's use English as an example. Generally, the longest common prefix that you will find on average in the English language will be around about a max of 7 characters. And then, knowing this, we know that the height of a binary search tree in this case would be 14, for example, for 10,000 English words and 17 for 100,000 English words. And in case of the trie, if your longest common prefix is 7, you know that the height will be 7 plus 2, 9, which is clearly much less deep than BST. And of course, the more shallow your trees are, the faster you'll be able to actually search them. So yes, tries are more efficient than standard binary search trees. However, you might still feel that tries are wasting space. I personally feel that way when I look at all of this alphabet represented many times over in every single node. Clearly, well, yes, storing the entire alphabet in every single node, first of all, allows you for an easy implementation with an array of a fixed size, and of course it allows you to encode any possible combination of characters. However, in reality, obviously not every single permutation of characters yields useful words, so in reality most of your characters inside of the individual nodes will have null pointers, so you store a whole bunch of useless null pointers. What can we do to avoid that? Well, the solution should be quite obvious, right? If we feel that storing the entire alphabet in every single node is a waste, then how about we only store the characters that actually do lead somewhere, that are associated with other nodes or leaf nodes that are associated with valid keys. So for our previous example, this is how much smaller it will look. In this case, I have only kept the characters that are in fact associated with non-null pointers. Of course, the convenience of a fixed size array is gone, so if you are adding more words, you have to maintain these little structures of pointers, and in order to do it in order to make it more doable, easier to work with, it's a good idea to replace arrays with linked lists. In this case, if you realize that you have to insert something new that's not currently covered by the characters that you store per node, you can always just in an alphabetical order insert an extra character inside of your linked list without disturbing the rest of the structure. So the most compact will be the one that uses linked lists instead of fixed size arrays inside of the non-leaf nodes, and for the leaf nodes it should then only store the suffixes, not the entire keys. That way you can really only store what's necessary. Turns out that you can in fact compress the tries even further. There were a couple of different attempts. Let's just discuss a few, because of course efficiency is something we care about very deeply in course 2 and 2. An interesting concept is the concept of ad ergo tries. Ad ergo is just a Latin word for in reverse, and the idea behind ad ergo tries is that you actually insert words in reverse. So instead of inserting beer, I would insert reeb, R-E-E-B. Instead of inserting B, I would insert E-E-B. So you always start at the end, you insert them backwards. Why is this a good idea? Well, as you probably know, words typically have lots of common prefixes. Words quite often have a common root, and certain roots can basically yield multiple different words. So essentially, inserting words in their normal order is almost guaranteed to yield long prefixes, long common prefixes. And long common suffixes are actually a lot less common. Of course, it's not going to completely eliminate the problem. You will still find common suffixes such as ality, for example, duality, rationality. There are lots of words that end in those particular 5 characters. So that is a common shared suffix. However, these are actually usually less long than the common prefixes. So on average, tries at ergo tends to be more compact than standard tries. Another interesting idea is to not actually create a tree structure at all, but rather, almost similar to heaps, to use arrays to store this entire thing and somehow pack the arrays as much of information as you can. Let's do a specific example. This one is borrowed from the textbook and it's a little bit mind-boggling, but anyway, this is what has been suggested and implemented in practice. So what we want to do is we want to actually not store these individual nodes. Rather, we want to create 2 arrays, where one array, cell array, basically stores all the data, and the other array, the try nodes, stores the pointer to the beginning of each node stored in this array. What exactly is happening inside of my cell array? Well, I will take my try and in this case assume that every single node is a fixed size array where the entire alphabet is stored, right? Of course, that will leave a lot of gaps. In other words, characters that are not associated with any useful pointers. Gaps are characters associated with null pointers. So what we are going to do is we're going to try and fill in those gaps by interleaving the individual nodes. So in this case, let's do this example. In figure A, you see the standard try where the entire alphabet is actually stored. So, as you can see in the root, we only have A and R associated with something. So we are then going to go ahead and store P1 and P2 in their correct positions in our cell array. This large array that is supposed to store all of the data. Then we take the second node, let's say we just do a breadth first traversal of this try, and we try to insert it into the cell array. And because my second array in this case starts with 2 gaps, I can actually push those 2 gaps all the way up to my first array. So I can kind of interleave the 2. As you can see, well, in fact, P2 is actually placed in between P3 and P4 just because I want to waste as little space as possible. And so we can carry on and sequentially insert all of the individual nodes of a try into this long array of all the data. So for the last one, again, we have 2 gaps in front of P6, which means that those 2 gaps can kind of be interleaved with P4 and P5. Of course, the assumption here is that you will not be inserting into a try. This kind of assumes that your try is already set in stone, you already know what your gaps are, the gaps are not going to change necessarily. Alright, so and then the try nodes will be responsible for knowing the beginning of each of these nodes. There are also more advanced algorithms for interleaving. In the first example, we did a sequential interleave where the nodes still follow each other. You can also mix them up in a more complicated way. In this case, let's say P1 and P2 still goes into the beginning of the cell array. Then my second node is actually going to be placed after P7, right? Yes, after P2 it's placed. And then the yellow nodes, P6 and P7, can actually be inserted kind of right onto the blue node P1 and P2. But as you can imagine, this becomes very, very complex very, very quickly, and I do not think this complexity is truly justified, because if gaps is what bothers you, then why not give up the fixed array size idea and rather use a linked list for individual nodes? In my opinion, the linked list solution is a lot more efficient, it's a lot smarter, it's easier for us to read and to maintain. So for your information, compression algorithms have been suggested, but in my personal opinion, simply replacing your fixed size array with a linked list is a much more viable, much more workable solution. Alright, and this is all you need to know about tries. I hope this made sense. Please feel free to ask questions on the discussion boards, email me personally, or talk to the tutors. Thank you very much.